Hello everyone, this is Mr. Kaviani, and by the end of this video, you should be able to break a vector into x and y components, describe the direction of a vector in terms of compass directions, and calculate the magnitude and direction of the resultant vector given two or more vectors. So what is a vector anyways? Well, by now we're familiar with the idea that a vector quantity is a quantity that has both a magnitude and a direction. Now, when we draw diagrams, we can represent vectors with arrows, where the magnitude of the vector is represented by the length of the arrow, meaning longer arrows are a higher magnitude or larger magnitude, and the direction of the vector can be represented by the angle at which the vector is drawn. And so, for example, on the right-hand side, I have a displacement vector shown here. This is vector A. This is potentially a vector showing a magnitude of 30 meters at an angle of 25 degrees north of east. So the magnitude here is the length of that arrow, we'll say 30 meters, and the direction would be 25 degrees north of east, just as an example. And so if you remember the treasure hunt lab from our class, essentially what you were doing was creating multiple displacement vectors. Now, let's take a look at this compass direction in more detail. Now, some nomenclature for how we represent the direction of a vector. The pattern when you report the direction will be like this. It'll be the degrees, the angle, and then it'll be your first direction. This is the direction you are going towards. Okay, and then the second direction is the direction you are starting from. So starting direction, essentially. Okay, let's look at an example of this. So vector B right here, this is vector B on our diagram on the right side. Vector B is 21.4 degrees, and then the directions, I start south, right? And I am going from south, I am going towards the east. See how that works? So I'm going towards east from south. So the going towards is the second one, and the one we start at is the first one. So that would be 21.4 degrees east of south. However, that also means that vector B is 68.6 degrees south of east. And so I would show that here, south of east. Again, the second one is the one I start at, so east, and then go towards the south, right? That would be that 68.6 degrees. So they form a 90-degree angle, so they're complementary of each other. You can use either one to represent that vector. So then applying that to vector C, vector C is 42.1 degrees north of west, right? Because I start west and I go towards the north, okay? That would mean vector C is also, right, 90 minus 42.1, that's going to be 47.9 degrees going towards the west from north. So that would be west of north. So make sure that you're comfortable reporting the direction of a vector given the two nearest compass directions. So now that we know what vectors are and we know how to report their directions, how do we add them together? Well, we add vectors from head to tail. Meaning if I take the head of one vector, like for example on the right-hand side, I take the head of A and connect it to the tail of B. That would be A plus B. And we call the sum of two vectors the resultant vector. And if I were to draw the resultant vector on my diagram on the right, you would begin at the very first point, so where A, the tail of A, and then go all the way to the last point. So in this case, that would be up here, the head of B. And that would be what I call my resultant vector, or a capital R for short. Okay. Now, the individual vectors, both A and B, are known as the component vectors, right? Those are the vectors that make up R, the resultant vector. Now we have two methods to calculate the resultant vector. The first is graphically. And so you see on the right-hand side, if I actually were to measure these, put them on graph paper, I could measure r and actually get the calculation for r that way. But we also have an algebraic and trigonometric way. So I'll say algebraic plus trig. And we call this component analysis. And this will be the method that we use in this class. So when it comes to vector components, we can actually split any vector at an angle, so one that's not perfectly horizontal or vertical, into what we call horizontal and vertical components. So if this happened to be, we'll just say this is a displacement vector of 75 meters, and we'll say that the angle above the horizon here is 30 degrees, right? Then we can actually split this vector into its components, or into the two vectors that make up this vector. And so what I can do is I'll show the horizontal component in red. I'll start here and show the horizontal part of this vector in red. We'll call this, if we call the big vector A, then this could be A sub x, right? And then if I show my vertical component in green here, this could be my A sub y. And so A sub x would be my horizontal component, and A sub y would be my vertical component of A. And so essentially we can take any vector, and that vector becomes the hypotenuse of its own right triangle, right? This will be a right triangle. So to solve for A sub x and A sub y, right, the horizontal and vertical components, we can actually use our trigonometric functions. If you're not familiar with them, we've got sine, cosine, and tangent. A helpful tool to remember them is SOH CAH TOA. And so we can use these functions to determine what the actual magnitudes of the components will be. So in this case, the SOH in SOH CAH TOA means that sine is the opposite side of the triangle over the hypotenuse. Cosine, and I'll put the theta in here. This is sine of theta, cosine of theta. So cosine of the actual degrees of the triangle would be the adjacent side, right, over the hypotenuse. So we have the S, the O, and the H, the C, the A, and the H. And then tangent of theta would be the opposite over the adjacent side. So we have the T, the A, the O, and the A. SOH CAH TOA. Now if I were to apply that to my triangle, then this side right here, this A sub x, is adjacent to this angle theta, right? So if this is my theta, then I could say that cosine of theta would be equal to the adjacent side, A sub x, over the hypotenuse. In this case, we'll say that's just 75 meters. This is an example. We would be given that magnitude usually. So then if I were to rearrange for A sub x would be 75 times cosine. In this case, theta is 30 degrees. And that would be my horizontal component here. Okay. Now, if I were to solve for the vertical component, A sub y, I could do, sine of theta, right? Because this is the adjacent side. So this is the, opposite. This is the opposite. This is the adjacent side of my triangle. And this is my hypotenuse. So sine of theta would be the opposite side. That would be my A sub y over my hypotenuse, 75 meters in this case. That's just what I'm given. And that would mean that if I were to multiply by 75 on both sides, that A sub y would be equal to 75 times sine. In this case, it's 30 degrees. And that would be my y component in this problem. So again, this is just an example. You'll be given the magnitude of the hypotenuse typically, right? And then you'll break that into components. You can use sine and cosine to help you do that. Please watch the next video to see an example of vector addition.